Hey team, this video will look at component 3 from the Unit 1 practice SAC on relations, polynomials and functions. I want to start off by apologizing and stating that there was a typo in this. This should have been 1 divided by 100 as the leading coefficient, but we will have a quick look at what it means when it's 500 and go from there. The big issue in this problem is it's the temperature inside the case we made in component 2 is given by this function between 0 and 24, and we want to know when it returns back to ambient temperature, where this temperature is the temperature above ambient temperature. So I've already defined the function. If we go look at the graph, if we graph this, we will see that yes, it starts technically at H equals 0, the temperature is 4/10, so it is just a little bit above ambient temperature already inside the box. And then it rises up and then comes back down. And it does eventually go back down to ambient temperature and then really dives down. But that actually occurs at, if I trace the graph and will let me, yes, trace across, okay. That's happening around 90 hours. Now, the problem is to find between 0 and 24, so we have an error there. And that would have been fixed between 1 and 100. So let's go back, and the process you could have used to find the bisection, the intercept, is still the same, just where you started with what values you picked would have been really hard to do because the domain you were given wouldn't have given an actual answer. So that's an issue. So let's go back to main and change our function to be -1 on 100. Define, run that. Go back to the graph, regraph, and then if we zoom in there we go. We can clearly see that, again, we're starting at 4/10, so even though it looks like it's going through the origin, it's just technically above the origin because of the constant term. Goes up some value, and let's set our y scale to give us a better idea because it's currently set to 100. So let's set it to 1, okay, and let's do a bit of a zoom box. Okay, we're going to have to zoom out. There we go. We can see our scale goes up to 14 there, but we have an idea that clearly it comes down and intersects. And we need to find that point using the bisection method to the nearest 1/10 of an hour, so 1 decimal place. So how do we go about that? We're using it as 1 T of H is equal to -1 on 100 H cubed plus 9 on 50 H squared plus 4 over 10th. And we're given our domain. What we want to do, because I haven't told you to look in a specific spot, I just want to know when's the next time it goes down. What you'd realistically want to do is set your left and right margins that you're going to start looking in as 0 and 24 and see what the graph is doing. Okay, so if we go in and do t of 0, t of 24, we will get, if we go back to main, and this is where defining the function is really handy, because we can just put 0 in there and we get, okay, so we get 0.4, which we knew, but it's positive. Okay, at 0, and then at t at 24, put 24 in our calculator. Let me type 24. We get negative 34.16. So we're getting a negative value. And let's go a different color. So we're positive there, and we are negative at 24. So we want to split the bisection method. So we next want to check t of 12. So, and I called it h, which is a silly thing to do since that's the actual x variable in our problem, but let's redefine that so we don't run into any more issues. T of 12 okay, is 9.04 equals 9.04. So it's still positive. We're still positive at 12, so our line is above the x-axis and down over here. So we split again. So halfway between 12 and 24 is 18. Okay, so let's do t of 18. We get 0.4. Oh, we're getting pretty close now. Okay, still positive. Still positive. We've been positive all the way along. So we want to go halfway by section method. So 22, we want to count. And we, especially seeing t equals 0.4 and down here at t of 24 was negative 34.16. We're likely going to be in here. We're likely going to be really close to the 18, but let's keep doing the bisection method of splitting for now. So let's go t of 22, not 20, should go t of 21 to split, if I can actually do some mental arithmetic. T of 21 is negative 12.83, so we are negative here. So try in the middle again, which is 19.5. 19.5. Okay, so at 19.5, t of 19.5, we are negative 5.3. Okay, so since we are only going to the nearest tenth of an hour, or one decimal place, even halfway between 18 and 19.5, what will that be? That'll be 18.75. We don't do the 0.75. We don't go to 18.75 because that's two decimal places. Either pick 18.7 or 18.8. Now I'm going to take a nudge on 18.8. So let's try that. 18.8. Okay, still negative. Still negative. So t of 18.8 is negative 2.42. So still negative. Okay. So let's sort of think about what we're doing. We know 18 is positive at 0.4. We know 18.8 is negative at what we get. A negative at negative 2.42. Okay, so let's try 18.4. Split them. Split again. Gotta stop. Gotta actually click on the calculator. 18.4. Okay, still negative. Negative 0.95. So split in half. 18.2. Run negative, still negative, so that gives us 18.1, which is positive. Okay, so 18.1 was also still positive at 0.07239, and 18.2, I need to go back and actually write what that was. So t of 18.1 is equal to 0.07239. T of 18.2 was negative 0.262. The one that's actually closest to 0 is this one. So we could say h equals 18.1 to one decimal place is when it returns the ambient temperature. Now we need to make sure we answer the question that's explicitly asked. Okay. She wants you to find what time, okay, and that means like time of day. So we were told if we clear some of this to read the problem again, temperature H hours after being turned on at 8 a.m. Okay, so it's actually turned on at 8 a.m. That's when H equals 0. which is a bit weird being 8 a.m, but we've got to pay careful attention. So H equals 0 is 8 a.m. We've gone another 18.1 hours. So it's probably best to work in 24-hour times. 0800 plus 18.1. 8 plus 18, that takes us to 26.1, which is technically actually 02 into the next day, 0.1. So, and this is really weird to write it, but it would be returning to ambient temperature at 2.1 a.m. the next day would be the answer. And that's to the nearest tenth of an hour. It's a little bit weird to write it in tenths of an hour rather than in minutes. Okay, but 0.1 of an hour is 60 minutes, so that would be the same as 2:06. A tenth is 6 minutes, so it would be the same as 2:06 a.m. Okay, but it technically says to the nearest tenth of an hour, so you need to give it as a decimal rather than actual time. So 2.1 a.m. the next day is the answer to component 3. A little bit shorter than the other components. Just plugging away values in your calculator, really. That's it.